ICDCS SpotTune leveraging Transient resources for cost-efficient hyperparameter tuning in the public cloud. Abstract: hyperparameter tuning HPT is crucial for many machine learning algorithms, but due to the large search space, HPT is usually time-consuming and resource-intensive. Nowadays, many researchers use public cloud resources to training machine learning models. Convenient yet expensive. How to speed up the HPT process while at the same time reduce cost is very important for cloud machine learning users. In this paper, we propose a SpotTune and an approach that exploits transient revocable resources in the public cloud with some tailored strategies to the HPT in a parallel and cost-efficient manner. Orchestrating HPT process upon transition servers. SpotTune uses two main techniques: fine-grained and cost-aware resource provisioning, and the machine learning training trend predicting to reduce the monetary cost and runtime HPT processes. Our evaluation shows that SpotTune can reduce the cost by up to 90% and achieve a 61 performance cost rate improvement. Index terms: cloud computing, transition resources, hyperparameter tuning, machine learning. Introduction. Machine learning has become an important workload for the most research and the industry that tries to run insight from the collected dataset. A machine learning model usually consists of a set of parameters, which can be updated during the training process. Yet there are also some non-trainable parameters that need to be determined by developers before training. For example, number of hidden layers, learning rate, degree of regularization, kernel functions of SVM, etc. Namely hyperparameters in order to predicting outcomes for new coming data items more precisely. Developers need to repeat the training process with different hyperparameter HP setting until getting the optimal models. This trial and error procedures is called hyperparameter tuning (HPT). Tuning hyperparameters for a machine learning model is resource intensive and expensive, requiring trying models with different configurations. The emerging public cloud has unlimited computation capacity. Facilitating many developers to do HPT is parallel by renting a set of machines, which is convenient and fast but very expensive. Many cloud vendors offer a great opportunity: transient availability of cheap but revocable resources. 1 and 2, for example, AWS Spot instance and third and Google Cloud primitive resources. First, often provide users with a machine at 70% to 80% discount compared with the regular price of the on-demand instances, but with the risk that some of them might be taken away at any time. Intuitively using the dynamic resources to the HPT in parallel, i.e. launching a bunch of the transition servers simultaneously. Each of which tries a different hyperparameter setting, could be both fast and cheap, but to use it robustly and efficiently, there are three key issues to consider. Handle the interruption properly. Dynamic resources are cheap for a reason. They could be revoked at any time by cloud vendors, which they interrupt the machine learning training if no fault-tolerant strategies are applied. The intermediate training result would lose when encountering an interruption. Cost-aware resource provisioning. There are hundreds of instance types in the public cloud dynamic infrastructure market. each of which has a different price and computation ability. Besides, the price of transition resources is variable. Facing such complex cloud markets, the user could be confused about how to provision resources to reduce the overall cost. Make a full use of elasticity of the public cloud. The public cloud provides the ability of elasticity. Acquiring, releasing resources on demanding, and how paying for user computation capacity. HPT is well suited for this mechanism because after the exhaustive search of the hyperparameters, only a small part of the models will be left. If the models initiated with bad hyperparameters could be identified early, computation capacity could be released in time to lower the cost. To tackle the above issues, this paper describes for SpotTune, an orchestrating system that combines a fine-grained, cost-aware resource provisioning strategy with a machine learning training trend predicting method to leveraging transient cloud resources for HPT. SpotTune checksums the intermediate training data to the remote persistence storage when receiving the following the two principal techniques: fine-grained cost-aware resource provisioning. SpotTune provisions resource for HPT jobs by computing the expected cost at a fine granularity via predicting spot instance revocation probability and online profiling HPT job performances. SpotTune computes the expected cost of a single iteration in the next hour and select the instance that incurs the least cost to deploy the HPT jobs. Early shutdown based on training trend predicting. SpotTune models the training process as a predictable curve, predicting the training trend of the model using the metrics, for example, validation nodes, collected during the training. Generally speaking, it can judge whether a model is promising or not using partial metrics that could release resource running bad models in time. It just lets the model initiated with bad hyperparameters stop before they take more resources to do the unnecessary computation, denoted as early shutdown in this paper. This paper makes the following four primary contributions. It describes SpotTune, an orchestrating system that takes advantage of transient cloud resources to the HPT. It introduces a novel transient resource provisioning approach by computing the expected cost at a fine granularity. It proposed an enhanced spot instance revocation probability predicting method. It introduced a new machine learning model training trend predicting method, modeling the training process as a staged predictive curve. The remainder of the paper is organized as follows. Section 2 presents the background and motivation of this paper. Section 3 introduces the design of the SpotTune. Section 4 evaluate the SpotTune. Section 5 narratives some discussion of our system. Section 6 briefly introduces the related work. Section 7 concludes this paper, background and motivation. This section briefly introduces the background, including existing transient cloud resources market and their principal traits, hyperparameter tuning, and the motivation of the combining them together. Transitions clouding resources provisioned for business critical workloads could be available at a discount in public pay-as-you-go clouds, creating an opportunity for our workload. But those resources may be taken back when needed by cloud vendors again. Taking Amazon AWS EC2 Spot instance as an example, the subsection describes transition to cloud resources and the opportunity they provide us. The Amazon Elastic Computing Cloud, Amazon EC2, is a web service that provides secure, resizable computer capacity in the cloud. EC2 offers on-demand instances, which are reliable VM charged at a per second rate. Besides the reliable resources, EC2 also provides cheaper, usually 70% to 80% lower than the on-demand resources. You get primitive resources as a spot instance. Spot instance could be revoked at any time, thus providing users a trade-off between reliability and cost savings. There are several characteristics of the AWS EC2 spot instance that may affect the monetary cost and the possibility of revocation. First, different instance type have different spot markets. 1 and 2. Second, price fluctuations among different markets are barely correlated. Third, the user could specify a maximum prices when acquiring a spot instance. It could be considered as a maximum prices the user would like to pay for it. Once the spot market price is over the user maximum prices, the instance would be revoked by the AWS. First, the user is charged at a per second rate with the spot market price, not the maximum price. With an exception, user can get a full refund if the acquired instance is revoked in its first instance hour 6. Besides, AWS provides a service that delivers termination notice 7, which are issued 2 minutes before the interruptions. Otherwise, there is no fund. In fact, AWS used the term bid before 27 replaced in the maximum price after, but the refund mechanism still exists. Figure 1 shows an example of spot prices changes over 11 days. Collect AWS spot prices. Spot prices instance type of R3 X large across 11 days. The uncharging on-demand prices of R3 X large is shown as well. Collectively, there are 2 kinds of strategies to the EC2 spot instances. The first kind of strategy bid carefully to minimize or mitigate the risks of being permitted. Gentle. Synthetically study the bidding strategies, deriving optical bidding strategies for different job requirements. Sharma et al. Present the notion of the sub-portfolios that is based on the financial portfolio modeling for reducing the effect of permission. Samai et al. Present SpotTune automatically select a spot market and fault tolerance mechanism to mitigate the impact of spot revocations. The other strategy is usually just a little higher than the current spot market price to maximize the odds of the being revoked within the first hour, thus enjoying the refund bonus. This kind of bidding strategy named as aggressive bidding. Harper et al. Present tributary borrowing to be permitted machines to satisfy a given service SLO with a lower cost. Hyperparameter tuning. An example of HPT. After the exhaustive search, only one optimal model is left. Here LR denotes a running rate parameter, DR a dropout rate parameter, sharp layer, the number of layers in the MLP models. Sharp input DIM, the dimension of the input data, and the feature, the number of the feature to use. Hyperparameter tuning of machine learning models. A machine learning model basically consists of a set of trained parameters, which could be updated during the training processes until the predefined model fits the training data. There are also some non-trainable parameters that should be determined by developers manually before training. Namely, hyperparameters. HPT is in fact a process of selecting the best model among the HP space based on domain knowledge and trial and error. Figure 2 shows an example of HPT. HPT can be done using the various searching algorithms over the space of hyperparameters, which means that the user launches multiple machine learning jobs, each performing full training using one hyperparameter settings, because the configuration space to search is usually large. This process is rather computationally expensive. especially in the context of the public pay-as-you-go crowd. Recent works 18 and 19 have proved the predictability of the machine learning model training, modeling the training process as a predictable curve. This mechanism could help lower the cost of the HPT if combined with the elasticity and the pay-as-you-go nature of the public cloud. That is, if bad models could be identified early by predicting the model quality with partially collected metrics, for example, validation nodes, the computation capacity could be released in the time. SpotTune follows this idea, modeling in the machine learning training process as a staged predictable curve to early release mechanisms running bad models. C. Tuning with the transition resources, inspired by the properties of transition cloud resources and the nature of HPT jobs. We present SpotTune addressing the issue of the transition resource opportunity, the cloud elastically, and the machine learning training predictably to orchestrate HPT upon transition cloud resources in a parallel and cost-effective manner. Section 3 describes the design of SpotTune. To our knowledge, SpotTune is the first system leveraging transitions resources in the public cloud to the HPT. Figure 3. SpotTune overview. SpotTune consists of two important components, the provisioner and the orchestrator. The former is used to interact with the cloud-acquired resources, and the latter is responsible for orchestrating the training processes. In this section, we detail the design of SpotTune. SpotTune has main concerns: finishing the HPT process with as low cost as possible, and to selecting near optimal models from all the HPs after fixing number of iterating steps. Overview. Figure 3 depicts a high-level view of SpotTune as its operational environment. In a word, SpotTune takes advantage of cheap transition resources and the elasticity of the public cloud to do HPT in the cost-effective manner. Note here that except for the machine learning model or the HP and the training data, the user additionally needs to specify for other important parameters as described in Table 1, which could be assigned according to the real needs. Provisioner. In the SpotTune interaction with AWS to request and require resources by computing the accepted cost according to the output of revision prayed and the online updated performance data. Provisioner chooses the proper instances to deploy HPT jobs. Algorithms. SpotTune workflow. Orchestrator is responsible for monitoring the training trend and then predicting the final metric of every HPT jobs using partially collected metrics. For example, validation nodes during the training and when revocation happens. Orchestrator notifies the VM to checkpoint the intermediate training result, the remote object storage S3. Algorithm 1 describes the entire workflow of SpotTune to run the HPT jobs of the machine learning algorithms. The expected cost in the next hour or for all the instances could be calculated using the following equation. Whether P is the revocation probability of the current instance predicted by revision predicted model, which we will introduce the detailed mechanism in the next subsection, and the price is the average prices of the instance in the last hour. Then function get best instance returns the instance that has the lowest step cost per step in the next hour, which is the monetary cost of running a single iteration defined as the following equations. where M is a two-dimensional matrix recording the performance of the running different HP on the different instances. For example, M x3 x large HP1 seconds per step represent the speed of running HPT jobs HP1 on instance x3 x large. M is initiated according to the number of CPU cores of each instances. During the HPT processes, M would be updated in an online manner according to the latest runs shown in line 36 of algorithm 1. This performance modeling method is practical because the computation pattern of the concrete HPT job is steady across different iterations, which we will demonstrate in our experiment, subsection 4A5. Then, as the line of the 16 to 46 of the algorithm 1 shows, SpotTune loops to wait for 3 events. When receiving the pre-delivered revocation notice from the AWS, SpotTune checks point its intermediate training result to S3 and arranges a redeployment. Second, when an HPT job finishes, SpotTune checks its intermediate training result to S3 and marks it finished. When an HPT job has run on an instance for more than 1 hour, SpotTune checks its intermediate training result and shut down the VM arranged for redeployment. As we analyze in section 1, HPT usually only leaves a small portion of models after trying them all, which means that a large amount of computation is meaningless. So SpotTune would not finish all the training steps. It would stop at setup times max trial steps and predict the final quality, for example, validation loss of every models. After that, it would continue the training of the top recent model from the checkpoint. Line 48 to 53 reveals this procedure. An example of the lifetime of an HPT job using the SpotTune. Figure 4 depicts a typical example of the lifetime of the HPT job in SpotTune. As the demo figure shows, the VM that the model is deployed on the revoked in the less than 1 hour, so the initial tens of the minutes are free. Then SpotTune forwardly shut down the model training process when it has not been revoked for more than 1 hour. And when the model has been trained for setup max trial steps, early COPS determines whether to finish the entire training. According to the algorithm 1, the functionality of the SpotTune is guaranteed by two important prediction models: revision period line 5th and early COPS line 15th. We show the details of these two models in the next two subsections. Spot market pricing, spot market price modeling. As equation 2 shows, the revocation probability is one of the factors that SpotTune uses to calculate the step cost. Given instance type 1, a maximum prices B and the timestamp T, revision period could output the revocation probability PIBT of this instance in the next hours. The hour it is, the more possible SpotTune may select it, similar to tributary, which is the state-of-art spot instance revocation probability predicting algorithms. Revision period use an LSTM-based deep neural network model structure to extract the history price knowledge. But the revision period, there are two main differences. The LSTM structure in the rev period only handles partial input data. Revision period adopts different data pre-processing approach to generate the maximum price. For each individual spot market, an independent model is trained offline using the history spot price dataset. The input data of our model is separated into two parts. The first part is the history prices across the past 59 minutes, with each price recording containing the following 6 engineered features. First, current spot market prices. Second, average spot market prices. Third, the number of price changes in the past hours. First, the time duration since the current spot market prices is set. Fifth, whether the time is the workdays or not. Sixth, current hour of the day. The second part is the present price record, with the above 6 features and the maximum price. Intuitively, the maximum prices is randomly generated when the training is an STM model, which is slightly higher than the present spot market prices by the random delta in a predefined interval 0.0001, 0.2. While revision period, we argued that the delta should be determined differently in training in the inferences. When training the model, the maximum prices bit at the time t is determined by the market price fluctuation as algorithm 2, aiming at calculating the average variation of instance i's history prices, removing the smallest 20% and the largest 20% in the previous 1 hour as deltas in the training data. This data comes from the essence of the active learning, which suggests that the data point locating on the classification border would help improve the model most significantly, and intuitively the average variation of prices plus the current price would be close to the border of the separate revoked and non-revoked. If the spot market prices grow over the maximum prices in the following 1 hour, we label this record as true, while using the trained model for inference. Level period randomly generate the maximum prices bit as the tributary does. The prices recorded in the past hours are fed into the 3-tier LSTM structure to retrieve the history spot market information, coming out as an embedded feature vectors. The present price record is converted to an embedding presentation to through 3 sequential fully connected layers. Then these 2 features vectors are concatenated together to come up with a probability-like result. The spot market price data could be very secret. We use 2 techniques to mitigate the data imbalance issues. First, we carefully design the loss functions by assigning different weight for different classes. Less theta and theta denoted the percentage of the positive samples marked as true and negative samples in the training set. Then we assign theta, pi, and pi plus as a positive and negative class weight. Second, we do not use the output of a prediction model as the probability directly, denoting the output of the model for I with the price B at the time t as p IBT. We compute the preemption probability IBT as once the live-pred model is trained using the history price data of instance I. It could predict the probability of preemption IBT is in the following hour given the timestamp and the maximum price. The machine learning training trend models only cover using partial metrics to metric the final metric of the machine learning models, thus to save computation capacity by logistic regression validating every epoch curves of the epsilon data using the 3 different hyperparameter settings, where bits denoted the batch size, IRR the initial running rate, DR the decay rate of the running rate, and DS the running of the number of the steps between 2 running rate decay. B RSNet 56 validation of the CIFAR R10 dataset. This model applies the running rate that decays periodically such that the validation curve is separated to 2 different stages. Shutting down bad models early, the user could indicate different metrics for the different programs. For example, training, validating, cross entropy for classification programs, and training, validating MSE, mean squared error. For regression programs, the algorithm and metrics used in our experiment are shown in Table 2. Machine learning algorithms listed in the Table 2 use gradient-based optimization approaches to update training parameters, which converges. Assume the loss function f is convex differentiable and vector f Lipschitz continuous of the order k per 1 in terms of the number of steps k, with optimized version of the gradient descent boosting. The convergence rate could be improved to order k square per 1. Figure 5 shows an example of the different shapes of validation loss curves using the different HP settings. Early curve use the following models algorithm optimized with optimizers that converge at the different rate are discussed in section 5 to fit the validation metrics during the training processes. Whether denotes the model predicted metric at the